Hello my friends and welcome back to the Today Machine channel. The stranding machine is a sophisticated cable production machine designed to twist multiple wires or strands together to create high-quality cables used for electrical power transmission. This machine is crucial in meeting the growing global demand for renewable energy and supporting energy networks that require safe, reliable, and stable cable infrastructure. The machine operates with precise engineering expertise to ensure the efficient production of various cables, including high voltage, medium voltage, and low voltage cables, tailored for complex energy systems. It allows for the production of cables that can withstand unpredictable energy flows, critical for renewable energy sources like wind and solar. The machine is part of a broader system that offers intelligent cable solutions, from connection technologies to worldwide maintenance, ensuring the reliability and sustainability of power networks. The machines are used by power cable manufacturers to produce cables that meet modern energy transmission needs. The armoring line is an essential part of the cable production process, adding protective layers to cables to ensure durability and resistance to external stresses. The line includes the self-traversing payoff, capable of handling 40-ton coils, which feeds the cable into the system. A tangential taping head applies a layer of tape for insulation or shielding. The rigid strander twists wires together for structural integrity. While another rigid strander is often used for additional twisting, the steel taping head applies a steel tape for mechanical protection, followed by another tangential taping head for final layering. The haul-off caterpillar moves the cable through the system, and the process concludes with the self-traversing take-up, which winds the finished cable onto reels, also capable of holding 40 tons. This ensures that the cable is ready for use in demanding environments. Wire manufacturing at Pacer begins with finely stranded, tinned copper conductors. Feeders guide the conductor off the reel and into the crosshead, where the insulation process begins using a PVC compound. Resin pellets are first added to the hopper, and the PVC compound is mixed with a precise ratio of colored resin. This mixture then flows into the extrusion machine. In the extrusion process, the compound moves through the crosshead, where it is evenly applied over the copper conductor. A crosshead tip ensures that the insulation fully encases the wire. The newly insulated wire is then cooled as it enters a water trough. While still warm, the wire passes under a print wheel that applies a legend indicating UL and CSA compliance. The ink dries quickly on the hot wire. Next, the wire goes through a laser micrometer, which checks the diameter of the wire multiple times per second to ensure uniform thickness. After this, the wire continues to cool in a second water bath before entering the spark tester. This critical step tests the wire's electrical integrity by subjecting it to thousands of volts as it passes through beaded chains. Once tested, the completed wire is gathered onto large master reels. It can either be spooled according to customer specifications or used in the production of Pacer's boat cable range. This process ensures that the wire produced is safe, compliant, and reliable for its intended applications. We are now in General Cables Factory, a leading global producer, serves as a key player in the energy, industrial, specialty, and communication markets by manufacturing high-quality wire and cable products. The manufacturing process begins with selecting the conductor material. The primary materials used for conductors are copper, aluminum, or optical fiber, depending on the specific application. Each type of conductor has unique properties that make it suitable for different tasks. Copper is the most commonly used conductor, valued for its excellent electrical conductivity. The copper manufacturing process starts with extracting the mineral from the earth in its raw form as copper ore. The ore undergoes several refining steps, including crushing and smelting, to extract pure copper. The refined copper is then formed into rods, known as copper cathodes. These rods are either sold to cable manufacturers or used internally within General Cables facilities for further processing. The copper rods are reduced in size using rod breakdown machines to the appropriate gauge for wire production. Aluminum is another important conductor material, especially in applications where weight is a concern. The aluminum goes through a similar process of extraction, refining, and forming into rods, which are then drawn down to the required size for wire manufacturing. Optical fiber, made from silica or glass, is used for data transmission. Unlike copper and aluminum, optical fiber transmits data via light signals with minimal electromagnetic interference, making it ideal for telecommunications and internet applications. After the conductor has been drawn and stranded, the next step is applying insulation. Insulation serves as a protective barrier that prevents electrical leakage and protects the wire from external damage. The insulation material is typically applied using an extruder, which heats and compresses the material into a molten state before coating the conductor. The most common insulating material is polyethylene, PE, known for its flexibility and durability. However, other materials such as PVC, polyvinyl chloride, and rubber compounds are also used depending on the application. Rubber compounds, for example, offer greater flexibility and are often used in industrial cables. General Cable uses advanced rubber compounding lines to produce a variety of rubber insulations in different colors. Once the conductor is coated, the insulated wire is passed through a cooling trough, solidifying the insulation and ensuring that it maintains its shape and thickness. Some wires are further cured in a continuous vulcanization process, using high-pressure steam or nitrogen. Once the conductor material copper, aluminum, or optical fiber is prepared, it is drawn down to the required diameter or gauge size. This is a crucial step in determining the wire's capacity to carry electrical current or transmit signals. Copper and aluminum rods are drawn through a series of dies to gradually reduce their diameter. Optical fibers are manufactured to specific tolerances to ensure they meet the precise requirements for high-speed data transmission. The drawing process must be meticulously controlled to maintain the conductor's mechanical and electrical properties. The drawn wire is then stranded or bundled, depending on the end product's specifications. Stranding involves twisting multiple wires together to improve flexibility, durability, and conductivity. Shielding and armoring. Many cables require shielding to protect them from electrical interference or mechanical damage. Shielding is especially important in cables that are used in harsh environments, such as underground or industrial settings. Shielding involves wrapping the cable in metal foils, tapes, or braided wire to block electromagnetic interference, EMI, which can distort signals. For certain applications, General Cable adds a protective shield made of materials like copper, aluminum, or bronze, which is either braided or applied as a metal tape around the conductors. For cables used in extreme conditions, such as in the oil and gas industry, additional protection in the form of armor is applied. Heavy-duty armored cables have a metal jacket, such as continuous corrugated welded (CCW) aluminum tape, which is welded and corrugated around the cable core for added strength. This makes the cable impervious to gases, liquids, and vapors, allowing it to function in hazardous environments. Conductors, commonly affected by crosstalk, rely on color coding for identification, which is crucial for cable installers. This coding helps differentiate pairs and units of wire. Some cables, like data communication products, may have as few as 4 pairs, while others, like telecommunications cables, can have up to 4,200 pairs bundled together. These stranded cores are combined by a cabler, often using binders, fillers, and tapes for cushioning and stability. A polyester core wrap offers mechanical protection, while dielectric layers between the core and metal shields provide further protection. Some cables feature coated aluminum tape to block external interference, and protective shielding adds strength and electromagnetic protection. Petroleum-based filling compounds are sometimes used to prevent water penetration, depending on the cable's application. Shielding encases the wires or cable to minimize electromagnetic interference (EMI), preserving signal integrity. Certain cables, designed for underground use, are shielded against damage from burrowing animals like gophers. Portable cords, used in temporary power applications such as construction sites and entertainment venues, have smaller gauge conductors and are wound onto metal reels before the cabling process begins. Color-coded conductors, commonly black, white, green, and red, are twisted together, with fillers added as needed to fill gaps. Depending on the design, tapes or cotton wraps may be applied to the multi-conductor cable. Different types of twisting machines, such as planetary and rigid BABA, ensure that consistent rotation patterns are maintained. General cables, industrial and specialty cables are used in a wide range of markets, including electrical power generation, oil and gas, mining, industrial automation, and military sectors. In addition to standard manufacturing processes, they employ advanced techniques like continuous vulcanization, radiation molding, and moisture cure processing. Cables may require braided shields formed from copper, aluminum, or bronze, and heavy-duty armor for extreme environments. CCW, continuous corrugated welded cables, designed for hazardous areas, feature an aluminum tape welded and corrugated around the core, providing strength and resistance to gas, liquids, and vapors. Energy cables produced by General Cable include low, medium, high, and extra high voltage power transmission products. These cables, often larger in scale, undergo similar manufacturing processes, except for bare overhead aluminum conductors. High voltage cables are made by drawing aluminum rods to the required size and stranding them according to precise specifications. The final stage of most cable production is the jacketing process, which adds an outer layer of protection, often made from plastic, rubber, or other compounds. Cable jackets are printed with a legend indicating important details like product designation, certifications, and traceability information, which may include a sequential footage marker for length accuracy. Throughout the manufacturing process, cables undergo rigorous testing, such as dielectric strength tests, to ensure they meet industry standards and customer specifications. Once completed, the finished cables are spooled onto large reels or packaged for distribution. The manufacturing process for ultrafine and conductive wires used in the semiconductor, electronics, and telecommunications industries involves precise control over precious metals such as palladium, platinum, and rhodium. These wires are known for their exceptional electrical conductivity, hardness, and ability to withstand high temperatures, making them highly suitable for critical applications. The process begins with the preparation of the alloy. Similar to a cook assembling ingredients, the material manager mixes the desired metals to form an ingot, tailored to meet specific application requirements. This ingot is then melted in a crucible at temperatures reaching 2,500 degrees Celsius. To prevent unwanted chemical reactions, the molten alloy is protected with a special atmosphere. Once fully liquefied, the metal is cast into a mold to form a solid ingot. The red-hot ingot is then forged to ensure that its properties are uniform throughout. Following this, the cooling process forms a cast skin on the ingot, which is carefully milled off to reveal the pure core. The bar is subsequently rolled, transforming a 30 centimeters section into as much as 20 meters of rolled wire. The wire at this stage is octagonal and must be further processed into a round shape. It passes through a pre-wire unit, where rollers with progressively smaller grooves gradually shape the wire into a perfect round. After a second heating process, the wire undergoes drawing, where it is pulled through a series of smaller and smaller holes in drawing dies. This thins the wire down to an astonishing 10 micrometers, less than a quarter the thickness of a human hair. Finally, the wire undergoes rigorous quality assurance checks for conductivity, hardness, tensile strength, and roundness. Once it passes these tests, the wire is ready for delivery to customers for use in their high-tech applications. Rope production for cableways, such as the one used for the Biswal Grande E5, involves manufacturing fully locked coil ropes. These ropes are produced by companies like Pfizer in Switzerland. The rope used in this particular cableway is 72 millimeters in diameter and consists of several layers of strands. Each layer, or stranding, undergoes precise and monitored production steps, ensuring the rope's strength and durability. Due to the increasing size and speed of modern cable car cabins, the performance demands on these ropes have risen. These ropes are custom designed based on parameters like braking strength, diameter, and weight provided by the client. Modern ropes can last up to 40 years and are now integrated with advanced components such as fiber optics and electrical conductors for transmitting data and power, making them multifunctional for both structural support and communication needs. The delivery and installation of the 48-ton Panorama Bond cable, a feat of heavy transport and logistics, manufactured by the Teufelberger Company in Lower Austria. This massive cable was destined for its installation at a high altitude of 1,950 meters above Schruns, a picturesque town nestled in the Austrian Alps. The journey, however, was anything but simple, with steep terrain, narrow paths, and complex logistical challenges presenting themselves at every turn. The massive cable, measuring 4,830 meters in length and weighing an impressive 48 tons, required intricate planning for its transportation. Spiegel Transport, a company from Tyrol specializing in heavy transport, was tasked with moving the cable from Lower Austria to its final destination on the Hochschoch mountain near Schruns. The total weight of the transport, including the cable's spool, exceeded 65 tons. Before embarking on the most challenging leg of the journey, meticulous preparations were made. Both the tractor unit, an Iveco Tracker 8x6 heavy-duty vehicle, and the low-bed trailer had to be equipped and secured for the demanding ascent. The Iveco Tracker, with its 700-horsepower engine, was chosen for its ability to handle such an enormous load on steep and winding alpine roads. The transport began in earnest, as the convoy, led by an escort vehicle, set off through the narrow streets of Schruns. This was no small feat, as the streets are often filled with local traffic, and navigating through them with such a massive load required precise coordination. The first challenge arose when the convoy encountered an oncoming truck that hadn't managed to clear the road in time. Fortunately, a strategically placed passing bay allowed the two vehicles to navigate past each other with only centimeters to spare. The team from Spiegel Transporte demonstrated their expertise at every stage. The driver of the tractor unit was responsible for managing the powerful engine as it hauled the massive cable uphill, while a second crew member controlled the trailer's axles remotely, via radio. This synchronized effort was essential for ensuring that the transport navigated the sharp hairpin turns and narrow bends of the alpine roads without incident. As the convoy ascended further, the terrain became even more treacherous. After navigating the asphalted sections of the road, the team faced the added difficulty of moving onto an unpaved gravel track. The weight of the transport required constant monitoring of the axle load to prevent excessive pressure on the gravel road, which could lead to tire blowouts or even cause the road to give way under the immense weight. At each hairpin turn, the convoy had to slow down to a crawl, losing precious time as the road was only closed for 4 hours. Despite the time pressure, the team maintained their composure, carefully maneuvering the trailer and load around each tight bend with precision. The steep terrain and narrow switchbacks demanded patience and skill from both the driver and the crew members guiding the transport. One of the most critical moments came near the top of the ascent, where the steepest section of the road awaited. To ensure the convoy had enough power to tackle this final challenge, a second truck was brought in to assist. The additional 500 horsepower provided by this second vehicle gave the convoy the extra push it needed to conquer the steep incline. With both trucks working in unison, the transport successfully made its way over the final obstacle. The Panorama-Bahn is a major construction project in the Montafon region of Austria, which aims to enhance the area's appeal as a leading destination for sports and tourism. The cable car, once complete, will be the longest in the Vorarlberg region and will feature 65 gondolas, traversing a 2,470-meter-long route. The transportation of the cable was a crucial phase of the project, following the successful installation of the supports and towers that form the backbone of the system. The unloading process involved the use of 2 cranes, one mounted on the Spiegel Transporte truck and another mobile crane from the Lustenauer company, Schäftknecht Autokran. The cranes were positioned on either side of the cable spool, lifting it carefully so that the trailer could be removed from beneath it. This delicate operation required precise coordination to ensure that the spool remained stable throughout the process. Once the cable was safely unloaded, the mission was considered complete. The team from Spiegel Transporte had successfully delivered the cable to its destination, overcoming numerous challenges along the way. The next phase of the project, the installation of the cable by the workers from Silvretta Montafon, would soon begin. The process of splicing the cable for the Panorama-Bahn is a physically demanding task that involves weaving the 2 ends of the cable together to create a continuous loop capable of transporting gondolas. After the impressive transportation of the 4,830-meter-long, 48-ton cable from Schruns to the 4th support of the new Panorama-Bahn at 1,950 meters, the splicing process began. This involves handling 3 different cables. The thinnest is flown to the site by helicopter and laid out, while the second and third cables are pulled using a winch. Each cable consists of 6 strands, which are untwisted, and then the ends are carefully woven back together to create a secure splice. This splicing task, part of one of the longest cable car systems in Vorarlberg, requires great precision and teamwork. A team comprising Silvretta Montafon employees, trainees, and technicians from the manufacturer Teufelberger worked together on this challenging task. They cut open the strands of the 52 mm thick cable over a length of 60 meters to complete the splice. Precise measurements are essential during the process, especially when it comes to distributing the splice length evenly to maintain the cable's strength. Despite adverse weather conditions, including rain and fog, the team completed the splicing in 2 days. One crucial aspect of the process is ensuring the cable doesn't become thicker at the splice point, which would weaken its performance. The final step involves using a rope spider to prevent the strands from touching each other, further increasing the cable's durability. Once completed, the cable will be capable of transporting 65 gondolas along the 2,374-meter line at a maximum speed of 6 meters per second, ensuring the new Panorama Bond can transport up to 2,360 people per hour. The fully automatic wire knitting machine is designed for efficient and continuous production of wire mesh in various sizes, with wire thicknesses ranging from 1.8 mm to 3.2 mm. It features a double wire entry roller system, which enables smooth feeding of wires into the knitting mechanism. The machine can handle wire widths up to 220 centimeters and can be adjusted for different pore sizes, making it versatile for multiple production needs. Key components include an easy mold change system and an improved reel adjustment system, allowing quick transitions between production configurations. The machine also incorporates edge bending, straight bending, and twisting systems to enhance the structural integrity of the finished wire mesh. A roll wrapping unit and both written and audible warning systems provide real-time feedback on machine status and performance. The PLC touchscreen panel enables operators to set key parameters such as knitting speed, wire width, and winding length. The machine can operate in manual, semi-manual, or fully automatic modes, offering flexibility based on production requirements. It is equipped with an automatic stop system that activates during wire insertion, jamming, or when the wire runs out, with both written and audible warnings alerting the operator. Other notable features include remote access for troubleshooting and updates via internet connection, a mold cooling system using a recirculating water tank to reduce mold wear, and daily performance tracking for production capacity control. The machine also offers enhanced safety with 4 separate safety systems and emergency stop buttons. Capable of 24-hour uninterrupted operation, this machine is ideal for high-volume, precise wire mesh production. The roll forging machine is essential for the pre-forging of metal rigging components, such as shackles, lifting hooks, spring hooks, snap hooks, swage sockets, and turnbuckles. These parts play a critical role in industries like ports, electric power, shipbuilding, petrochemical, and construction machinery. Roll forging enhances the mechanical properties of metal by improving its grain structure and creating components with greater strength and durability. The process involves shaping metal by compressing it between 2 rolls, allowing for precise and consistent preforms. This machine is highly versatile, capable of handling a variety of metals and component shapes. The resulting forged parts are able to withstand the extreme loads and harsh conditions typical in their applications, ensuring safety and longevity. The production of high-quality hair scissors begins with the 3D's design of the scissors. The steel is split to create individual blanks, which are then heated to 1040 degrees Celsius for forging. Forging under extreme heat improves the material's strength and ensures the durability of the scissors. Once forged, the contours of the scissors are cut, giving the blank its basic form. This process helps define the characteristic shape of the blades, handles, and finger rings. Precision grinding is applied to both the inside and outside of the finger rings, ensuring they are smooth and comfortable to hold. This is done using specialized grinding machines that work with micron-level accuracy. The scissors undergo heat treatment at temperatures above 1000 degrees Celsius to increase hardness and strength. After this, the blank is ice-hardened by cooling it to -180 degrees Celsius, further enhancing durability and resistance to wear. Machine grinding is used for initial shaping, followed by hand grinding for finer detailing. The pivot joint is ground for smooth blade movement, and the handle is shaped for comfort and balance. The surface is polished to achieve a smooth finish. If the scissors include thinning teeth, these are carefully eroded with precision to ensure even thinning performance. Each pair undergoes multiple inspections, including computer-aided fine-tuning, to ensure they meet design specifications. The scissors are assembled, and both the inside and outside cutting edges are meticulously sharpened. The tip is polished for precision cutting. The final inspection checks for cutting quality and smooth operation. Afterward, the scissors are laser marked for branding and batch tracking, followed by visual inspection and careful packaging. This combination of traditional craftsmanship and modern technology ensures the production of premium hair scissors with superior precision, sharpness, and durability. This 3D CNC wire bending machine, designed for straight cut-to-length wires, capable of creating a variety of complex shapes as per programmed instructions. This machine is widely used in the utensil industry, manufacturing parts like tawa handles, kadai handles, pan handles, and pot handles. It offers high accuracy and repeatability, making it ideal for producing precise parts consistently. Thanks to its automation and versatility, this machine is also suitable for applications in the automotive industry, where precision is key to manufacturing parts with consistent quality and tight tolerances. This powerful 3D CNC rod bending machine for handling cut-to-length rods with a diameter of up to 25 millimeters. This machine is equipped with advanced programming features, allowing users to input different axis coordinates to create a wide range of complex shapes. Its robust design ensures it can handle the toughest materials with precision and ease, making it the strongest machine available for bending 25 millimeters rods. It combines high speed and accuracy, significantly improving production efficiency. The machine is particularly useful for industries requiring custom rod shapes with high consistency, such as construction, automotive, and heavy machinery manufacturing.